Hello and welcome to my lecture series on Laplace transform. Now on today's lecture we are going to discuss about the Laplace transform of integrals. Right. In the last lecture we have gone through the Laplace transform of derivative, another very important property of Laplace transform. And so today let's go through how to find the Laplace transform of an integral. Now we start with the theorem of the Laplace transform of integral. This theorem it says that if Laplace transform of ft is known to be equal to f bar s, then we can find out Laplace transform of the integral 0 to t fu du. Okay, the integrand fu is actually the same function whose Laplace transform is known to you. So if you will be able to find out the Laplace transform of this integral 0 to t fu du, and that will be nothing but 1 by s into f bar s. Now more generally, actually the formula is used in the inverse sense. So if you take the inverse Laplace transform on both sides, you will get L inverse of 1 by s into f bar s to be equal to the value of this integral 0 to t fu du. So at times you may use this integral to find out the inverse Laplace transform, or in the reverse manner also. Okay. Value of the integral is used, or to find the value of the integral you need to let's say you know the inverse Laplace transform of f bar s by s, so the value of the integral is known. But more generally we try to find out the inverse Laplace transform by finding the integral. So this is another way you can remember L inverse of 1 by s into f bar s is equal to 0 to t fu du, a very important property in Laplace transform. Now we come to the proof of it. So we require to prove that L of 0 to t fu du is equal to 1 by s f bar s on the assumption that the Laplace transform of ft is known to be equal to f bar s. So what we do initially is that we assume the integral 0 to t fu du as fit, because it's obviously a function of t. So we take 0 to t fu du to be equal to phi t, and then we differentiate phi t with respect to t. So phi dash t we obtain. So phi dash t will be obviously ft, and phi 0 will be 0, because you see limits are same, so the area is 0. So phi 0 is 0, phi dash t is ft. Then what we do is that we apply the Laplace transform of derivative on phi t. That is, we try to find out Laplace transform of phi dash t. Now Laplace transform of phi dash t is s phi bar s minus phi 0, right? Because this is the thing that we have gone through in the previous lecture, Laplace transform of derivative. So we can use it over here because we have gone through it. So L of phi dash t is equal to s phi bar s minus phi 0. Now phi 0 is 0. So therefore your L of phi dash t is s phi bar s. But phi dash t has just now been found to be equal to ft. So in place of phi dash t over here, we can replace it by ft, because we have just now seen phi dash t is equal to ft. See here we just now have found that. So we can replace this phi dash t by ft, and on the right hand side we get s phi bar s, phi 0 being 0, which we have already observed. So ultimately what we get L of ft is equal to s phi bar s. Now L of ft is nothing but f bar s, and phi bar s is nothing but L of phi t. So I get f bar s by s is equal to L of phi t. In the very next step I have written that. So f bar s by s is equal to L of phi t. Now what is phi t? Phi t was assumed to be equal to the integral 0 to t ft fu du. So I just replace phi t by 0 to t fu du, and I get the result as required. So Laplace transform of integral 0 to t fu du is nothing but 1 by s into f bar s. So that is obtained. So if you take the inverse, then you can always use that in that way also. L inverse of f bar s by s is the value of this definite integral 0 to t fu du. So in that way also the property may be used. A very important property in the Laplace transform of integral. I hope you have understood it. Now on the basis of this property, let's do one problem. Like you see, you're asked to find out the inverse Laplace transform of 1 by s cube into s square plus a square. Now this problem may be done by other way, but I will do it in the manner by which I will be able to use this property which I have just now taught. So I want to find out 1 by s cube into s square plus a square. Now how I use this property over here? If you look at the result of inverse in the property is L inverse of f bar s by s. That is equal to integral 0 to t fu du, right? Where f is actually the inverse Laplace transform of f bar s, right? Now first of all, we know in this problem we know that the inverse Laplace transform of 1 by s square plus a square is very well known to us. It is what? It is 1 by a sin a t, right? So L inverse of 1 by s square plus a square is 1 by a sin a t. So if we now apply the Laplace transform of integral property here, that means if L inverse of f bar s by s, what should I get? I'm just dividing f bar s by s, so not by s cube. We'll do one at a time. So if you divide it by s, that means I want to find this L inverse of 1 by s into s square plus s square. That can be obtained because I have already found out what is L inverse of 1 by s square plus s square. So I integrate this function which I have already found out because I know this one, the standard form. So I have to integrate this 1 by a sin a t, 1 by a sin a u with respect to u from 0 to t, which I'm going to do. So I'm just applying the property integral 0 to t fu du. So the formula is being used directly, and now integration takes place. Simple integration. If you integrate sin a u, it is minus cos a u. 1a will come down, making it a square. So minus 1 by s square cos a u, limits are 0 to t. If we put the limits, and cos 0 is 1. If you observe the minus sign inside, so you get 1 minus cos a t finally divided by s square. But that's not the answer. That is the L inverse of 1 by s into s square plus s square. You need to find out L inverse of 1 by s cube. So that means what we do is now, since L inverse of 1 by s into s square plus s square is now known to me, I can apply the Laplace transform of integral property once more. That means I divide now the function as 1 by s into s square plus s square by s, which will make it L inverse of 1 by s square into s square plus s square. See, just exactly the thing that I told. And now that means you have to integrate this function that you have got, because this is the L inverse of 1 by s into s square plus s square. So I just have to integrate 1 by s square into 1 minus cos a u from 0 to t. So I just do it. Again, it's simple integration. So if I integrate, I keep 1 by s square outside. It is u minus integration of cos u is sin a u, and by a, because coefficient of u is a, so a comes down. So u minus sin a u by a, limits are from 0 to t. So I put the limits using the fundamental theorem. So I get 1 by s square equal to t minus sin a t by a, because lower limit is 0, and in this case the lower limit is 0 because sin 0 is 0. So I get t minus sin a t by a into 1 by s square. But that's not the answer. Still one step to go, because now I have got L inverse of 1 by s square into 1 by s square plus s square. Now again, if we apply that property of Laplace transform of integral, you will be able to find out L inverse of 1 by s cube into s square plus s square. Okay, so if you divide f bar s by s again and take this inverse, so you have to just integrate the function that you have just now got, because this is the inverse Laplace transform of L inverse of 1 by s square into s square plus s square. So if I integrate now this function, which I will do, I'll be getting the final answer. So it's 1 by s square into u minus sin a u by a du over 0 to t. So let's take 1 by s square outside. It's a constant, and integration is very simple. It's u square by 2, and integration of sin a u is cos a u. So cos minus cos a u. So minus minus will become plus, a will come down, makes it a square. Limits are to be put from 0 to t. So the very next step, I apply the fundamental theorem, and I get the final answer. That is, I get 1 by s square, t square by 2, lower limit is 0. Here in this case, cos a t, and lower limit is not 0, it's cos 0 is 1. So it's minus 1 by s square is coming over here. So I get 1 by s square into t square by 2 plus cos a t by s square minus 1 by s square. So that gives me the final answer of this particular question. So from this example, I think you have understood that how we are using the Laplace transform of integral to find out the inverse Laplace transform of function, because at times we may be able to find out L inverse of f bar s by s. That means I'm talking of f bar s by s simply because you know L inverse of f bar s is known to you. So if L inverse of f bar s is known to you, so why not apply f bar s by s formula? Because in that case you have to just evaluate the definite integral and you will get the answer directly. So in that way also you can use this property. So very important property of Laplace transform of integral that has been discussed in today's class. So that's all for today's class. I'll be back with more properties and theorems in my next class. Till then, thank you. Thank you so much.